Here I have pictured the function x squared plus 8x. Consider the region bounded by the graph of f, the x-axis, and the line x equals 6. I drew the function f in red, and we have the x-axis shown as well. Here's the line x equals 6. So these are the boundaries they're referring to. Problem wants me to divide the interval 0, 6 into 3 equal subintervals. So when they talk about the interval 0, 6, they're talking about this interval here. Its width can be found by what's called b minus a, where a is the left side of the boundary and b is the right side of it. Now, in order to find the width of the subintervals, we can use a formula. Delta x equals b minus a over n. This is for the subinterval width. So plug in the right side of the interval, which is 6. And then we'll plug in the left side of the interval, which is 0. And then we'll divide by n, which refers to the number of subintervals requested. They want 3 subintervals. So for this problem, n is 3. This reveals that the subinterval width needs to be 2. So I'm going to divide my interval into 3 equal parts. And I'm just going to put these stars there to show the boundaries of the subintervals. So there's going to be a subinterval from 0 to 2. And there's going to be one from 2 to 4. And another one from 4 to 6. Now, since this is a right-hand sum, I need to let the height of the subintervals be determined by the right side of the subintervals. So I'll place these stars at 2, 4, and 6, which are the right sides of the subintervals. Then what I'll do is I'll trace up from there until I hit the function, and then let that height determine the height of my rectangles. Traced up from 2 till I hit the function and let that set the height. Now I'll trace up from 4 till I hit the function, and that can be the height of my second subinterval. And then I'll trace up from 6 until I hit the function. And there's my third subinterval. Now I'll shade the subintervals in. Okay, so in this particular problem, the Riemann sum will be an overestimate of the actual area. The right Riemann sum is pictured above, and the actual area is pictured below. Let's now calculate the area of each of the subintervals. In order to do that, we need to know their width and their heights. So the width is just going to be delta x for each of them. So that's 2. But their heights are going to be given by f of 2, f of 4, and f of 6. I'll make a little chart to organize this. First, I'll say what the xi is. This is going to be the right side of the subintervals, which is going to be 2, 4, and 6. Then we're going to plug those x's into the function in order to determine the heights of the rectangles. So using the formula x squared plus 8x, I'll plug in a 2 first. That gives me 20. F of 4 is 48. F of 6 is 84. The delta x for each rectangle was 2, and we now just want to multiply all the rectangle heights by their widths in order to get their areas. So the first one has an area of 40. The next subinterval has an area of 96. And the last subinterval has an area of 168. At that point, I want to add all those areas together. And it's 304 units. Now that we found the right Riemann sum approximation, we'd like to find the actual area under the curve, which will be found by a definite integral. And we'll do an integral from a to b of the function. So our a is 0 for this problem, and the b is 6. So we'll go from 0 to 6 as our limits of integration. Then plug in the function formula. We now need to find an antiderivative for x squared plus 8x. So antiderivative of x squared would be x cubed over 3. Antiderivative of 8x will be 8x squared over 2. Move the limits from the left side to the right side. And then subtract big F of 6 minus big F of 0, where F stands for the antiderivative in the brackets. I get 216 units. And it makes sense that the right-hand sum would be a little bit of an overestimate of the true area, which apparently is 216.